Well, thank you all so much for coming today. We will be starting the seminar like in just right now. So welcome everyone and thank you so much for coming today. I am Fatih Aranolo. I am the coordinator of Mining Department Seminar Committee. The committee organizes the seminar series and invites speakers to come and address students, faculty, and interested industry professionals on a variety of mining-related topics. Since we are today hybrid on Zoom and in person, I would like to request that everyone in the Zoom keep their microphones muted during the presentation and unmute them only to ask questions during our QA session. Just a reminder to everyone, we are recording this session, so you will be able to view it on the department YouTube channel after the seminar has concluded. Today, we would like to welcome Professor Şebnem Düzgün. Thank you very much for speaking with us today. Professor Şebnem Düzgün is a professor and Fred Banfield Distinguished Endowed Chair of Mining Engineering Department at Colorado School of Mines. She has also joined faculty appointment in the Department of Computer Science at Colorado School of Mines as well. Dr. Duzgun has an international reputation for a broad range of topics, including big data and artificial intelligence in the mining life cycle, probabilistic modeling of engineering and natural rock slopes and the quantitative risk assessment, analysis and management of risks associated with geotechnical hazards and tailing dam failures, mine environmental monitoring using remote sensing, virtual, augmented and mixed reality and serious gaming for technical training and collaborative decision making. She authored 4 books and published over 250 papers. Dr. Şebnem Düzgün will be talking to us today about the very interesting topic, which is big data and artificial intelligence in mine safety. Without further ado, please welcome Professor Şebnem.
Thank you, Fatih. So before starting my talk, I usually would like to know my audience. So how many graduate students we have, and people in the Zoom, they can raise their hands. How many graduate students we have? Okay, pretty good. Faculty, I know my colleagues, but I want to know any faculty's involvement via Zoom. Is there any faculty involvement? Okay, we have 4 faculty here plus 3. And undergraduate students? Great. Undergraduates? Okay, great. Fatih, can you let me know how many undergrad students we have in the Zoom? Undergraduate.
Undergraduate, nobody raised, or maybe I missed that.
Okay. And industry representatives, I'm not expecting any industrial representative here, but maybe in Zoom.
3 so far.
Okay, great. So the reason why I'm asking is that I want to share my experiences in my talk and our models according to the audience. So I think that I have a very well mix of audience, which is great. Before starting my talk, I'd like to share my journey in big data and AI. First of all, these topics, I know that this is new, seems like new, but actually it is not new. I started working on these topics actually in 2000, immediately after I got my PhD, but by that time, it was not called AI or there was no concept of big data. So I'm going to explain in my talk why we are now putting more emphasis on the big data and why we need AI. And I'm going to show you some of our research, which are basically applications in mine safety. So as a data scientist and a mining engineer and geoscientist, applications of big data and AI is not limited to mine safety. Some of my research relates to sustainability, data-driven approaches in mining sustainability. Some are related to supply chain, and mainly gold and other critical minerals, supply chain and data-driven approaches in their use. And some examples from the other disciplines are application of these methods in geothermal. And so I'm currently running a project on predicting blind geothermal sites, for example. So if you want to learn more about these topics, just contact me. So today's focus will be on mine safety. So I did some courses and some, let's say, talks on big data. And I know everyone knows the concept of data. What do you know about data? What is data? Can anyone tell me what is data? Yep.
Systematic information.
Yeah, actually, we don't call information as data, but so you said systematic information. Actually, data is some facts. If it is not processed, it cannot be an information. And there is a pyramid, it's called data, information, knowledge, and wisdom pyramid. It's in the information science. It says that if you have data, you don't have anything in terms of information and knowledge. But if you process data, you have information, knowledge, even wisdom. So wisdom is, in scientific terms, rules, theories. So big data actually change the way that we are conducting science and we are conducting information extraction. Why? Because in the past, we were developing some hypotheses or we were doing some observations in the field and then trying to answer the questions. Nowadays, with the availability of big data, we are asking data to tell us hypotheses, tell us hidden patterns. That's the reason why big data is really, really important, because we're not only using our intuition, but we are also obtaining more knowledge, more information from the data. So that is the reason why big data is now important, but it is also different from the ordinary data sets because it has different features. So let's have a look at those features. First of all, big data is defined by different V's. Some people call it 3 V's, some people call it 5 V's, some people even have driven 7 V's. Whatever the V's, the 5 important ones are here. So let's have a look at them one by one. First of all, data is now really big in volume. Volume means like zettabytes, yottabytes. So the volume is increasing exponentially. So in 90s, we were in kilobytes, megabytes. In 2000s, we were in gigabytes, terabytes. Now we are in petabytes, but we are approaching to zettabytes and yottabytes. The other feature is velocity. Velocity is really important for us because since the data is really fast, it allows us to do some predictions, some analysis, either near real time or real time. So this is the actual value. For example, you will see so many big data applications in predictive maintenance Actually, this predictive maintenance idea is to do near real-time or real-time predictions, because you can get huge amount of data, easily process it, and then you obtain some value. You know, we are more interested in information knowledge. So we need really fast processing for this. Oops. The other feature is variety. It's not a single data anymore. We have structured data sets are databases that we used in the past. So all the mining companies, for example, they have their own database management systems. At mines, we have, for example, student information systems, which are fine. But now we have so many sensors, so many data sources that you cannot manage those data in the structured form. An example, if you are running an autonomous truck fleet with 25 trucks, usually every truck has over 500 sensors. Your 500 multiplied by 25, every second you are collecting that amount of information. You can collect it at every second, but how are we gonna process this data? Where are we gonna store it? And also the information, the data that we are collecting from these trucks are variable. These trucks have Velodyne sensors. Velodyne sensors are providing lidar data. These trucks have some sensors in their engines, and engine data is just a signal. These trucks have cameras, and those trucks are providing some camera information, okay? So we have images, videos, some kind of signals, some kind of multimodal data sets. It's sometimes not possible to structure the data. So mainly the frustration coming from big data applications is to manage these data sets, to curate those data sets so that you can obtain some information. The other feature is veracity. Veracity is related to uncertainty. So if you have structured data, if you put your data into a database management system, you have a quality control. Even the database management system itself has that quality control because you do some database management related quality checks. But now you don't have it. How do you know that the sensor is providing the right data? How do you know that the image that you collected is the right image? So the IoT stands for Internet of Things. Even everybody now is collecting data, but we are all censored, which is fine. But how are we going to convert that data into an information with that level of uncertainty is also a question. Oops, sorry. So the next, if you can handle these problems, then you can obtain great value from data. And this value could be information, knowledge. Actually, in information theory, there's difference between information and knowledge. But how you do that? You use visual analytic. So while Fatih was introducing me, he was mentioning that I use virtual reality, augmented reality, because these are the good tools of visualization. When you use these visualization, you can immediately grasp the information. That's the reason why I started working on this. And you can definitely obtain analysis of patterns. You frequently have heard about machine learning. Machine learning is not new, okay? But you need to use the right machine learning tool for right set of data to obtain patterns. That's the difficult part. And statistical learning is not that different from the machine learning. It's a different approach, but what you obtain is the patterns. And of course, you do prediction. So in my talk, I will explain mainly how we use prediction models in mine safety. But actually, my research covers all of them. Some of the analysis, some of the research areas that I am implementing these methods use all of them. So I was really lucky, actually, in my career. I started interacting with really a large number of researchers who are dealing with those problems early in my career. So all the methods that I will be presenting you is the product of interdisciplinary research. So data analysis and obtaining big data obtaining value from the big data definitely requires interdisciplinary research. It's a teamwork. You cannot do it on your own. So I'm having so many requests from the graduate and undergraduate students. They want to join. They always show the interest to join my team. So joining my team means that you will learn so many interdisciplinary topics with an interdisciplinary groups, and you're very welcome. But the process is actually not easy. Why? Because you need to understand the problem. In our case, mine safety problem. Okay, so any data analysis or any big data analytic process requires first understanding of the problem, which means that you need a huge domain expert. So you need to be really good in your own domain. So this means that as a mining engineer, you need to well describe the problem. Most of the time, what I'm seeing is that many companies have expertise in machine learning AI, but when it comes to its application to mining, if there is a disconnect between the domain and the data scientist, success will be really low. That's a known fact, okay? So the question is, how are we going to connect this link? So I'm going to show how we do it in my talk later on when I'm explaining the examples. But as you remember, I talk about veracity, velocity, volume. Because of these challenges, curating data for specific analysis is the main challenge. And for this curation, you need to have a domain expertise. So data science, you probably have heard about the term, right? So the data science is actually not a single scientist's job. Data science is the combination of domain expertise, computer scientists, and math. So if you want to be a data scientist who has an experience in mining, you should be willing to learn computer science plus math. And that's the reason why I'm here, because I exposed really early in those topics in my early career. And my aim is to introduce these concepts to geoscientists, mining engineering disciplines, because I think that this is my responsibility to my domain. So don't think that you cannot do it because you don't know computer science. You don't think that you cannot do it because you don't know math. Actually, you know math very well. The only thing that you need to is to establish some background in computer science. Establishing the computer science doesn't mean that learning some software, okay? For example, I'm seeing some students coming to me and saying that, oh, I want to be competent in Python. This doesn't work like this, okay? And I will explain why it doesn't work like that. So having understood the big data concepts, let's have a look at what's an artificial intelligence. So artificial intelligence is not a single, let's say, method. It's an umbrella term. So what you do is that with an AI, you can create predictive analytics. You can do some object detection. It's again prediction, but it is different. The data types are different. And you can do speech recognition. Again, the data type is different. And you can do some information extraction. Those are mainly pattern analysis, but you predict the pattern. So where do we use this? We use this in machine learning, decision making, robotics, planning, natural language processing. But in decision making, we never ever use AI's results immediately. There is always human beings in the loop. So actually, AI results are decision support. In robotics, we use full detection methods, and I'll show some of the examples of from our research. So vision research to be implemented in robotics is well developed, but other type of research and other type of technologies are unfortunately not that mature. The reason is the amount of uncertainty involved. And I will explain how these uncertainties result in mind safety issues. So here is the team. I apologize if I miss any team member. I'm really busy and my brain is sometimes burning. So if I miss someone, please show up and accept my apologies in advance. So I'm going to show 4 examples. Roof fall hazard detection is almost a complete work. And of course, when you start a research, it never ends. So this is not an finished research, but early findings reach up to a really good research results, which this is published. Methane prediction is a project which has been going on for a while. I will explain how we are using AI for real-time prediction. And sys-tem challenge was an old project, but still going on. I will explain it. And the bad vision is a project which has been going on for a while. So bad vision is supported by Alpha Foundation. Sys-tem challenge was supported by MINES and our resources. Methane prediction and roof fall hazard detection are funded by NIOSH projects. So let's see one by one roof fall hazard detection. So as you know, there is a huge trend in mining that we should use autonomy. This is fine. However, there are limitations. For example, we have limited applications in underground. It's not only for underground's attrition conditions, it's also related to the uncertainties. Because predicting roof fall hazards in underground is not easy. And of course, if you have swarm of robots in underground working for you, you need to be aware of the potential roof fall hazards. And roof fall hazards are one of the major geotechnical hazards in underground mines. So you don't want your swarms smashed by the falling rocks, right? So the question is, can we detect these potential roof falls so that these detection algorithms can be used in a fully autonomous robotic platforms? So this is, of course, a compelling question. So we started initial research, and this research will not end, but of course it will have some implications recently. I'll show one of the applications. The other, so to apply or to develop some detection algorithms for the problem, we realized that Eastern underground mines mainly having these problems. By the way, there are some chats. Can you follow him, Fatih? There are some messages in the chat.
Yeah, those
Okay.
when you ask the meaning of.
Okay. So we realized that there isn't huge research going on for the roof fall problems in the eastern underground mines. The main reason is horizontal stresses in that area cause severe ground control problems. And how the mines operate is that they have a team and geotechnical, usually geological engineers, go to underground, make an assessment and say that, okay, these are the dangerous areas, don't go there. So the question is, can we automate this process? Can we save these safety engineers? And to answer this problem, we went to the field and we observed what they are doing. So we realized that they are really good in recognizing these roof falls with their eyes. So if their eyes and if their analytical processing is good in recognizing roof falls, question is, can we mimic them? So what we did is that we attended the process with them and we learned and we realized that they use visual clues to understand the potential failures. Usually horizontal stresses create some features, very well-defined geometrical features. And we realize that if we take some amount of hazardous roof falls and non-hazardous roof falls, we can train the system and let the system to recognize. And of course, before doing it, we need to check what's the expert's performance. Are they doing good? So we implemented a statistical test and we selected randomly some places that are identified by the expert saying that safe and unsafe. And we checked whether these roof falls or whether these areas have distinctive roof characteristics. And statistical test says us that yes, they are distinctive. So these are some examples. This is an example of a hazardous roof and non-hazardous roof. You can even differentiate with your eyes that there is a specific difference. So we realized that experts are doing a really good job. So the next thing is we collected images from the mines, and you cannot directly use those images. Remember, I told you that you need to curate the data. So once even when we go to the underground mines, those mines are really huge openings, and we need to have an appropriate light source so that we can have the good images. We even develop a new setup so that we can have the good images. And then once we have the images, we need to curate those images. That is called data augmentation in image analysis. So what you do is that you rotate those images so that the system recognizes all kinds of images, and then you flip them and then you change their contrast brightness values so the system will recognize any kind of feed that you are providing. Once we do that, the other problem is that, remember I was telling you that AI is not new. Yes, it's not new. Convolutional neural networks are not new. However, the success is coming from large number of data. For example, all the autonomous cars are using a few millions of pedestrian, street furniture, and car and bike data. And all these works has been started 10 years ago. That's the reason why it is mature, because they have millions of data. For example, each time you you're asked, you're not a robot, you click on whether you have a traffic light or not, right? This is actually data collection for these image nets. Okay, so you're actually contributing to that. But in mining, we don't have it. We don't have this large amount of data sets. How are we going to solve the problem? So there is a technique called transfer learning. So you train one learning method based on the existing images, and then that image's information is transferred to your data set. That's what we use. And we actually use Google's ImageNet, which has around 1.2 million of data. Those include medical images, other type of images, but these images have different features that could be recognized. So we relied on our network on already developed some features by Google's ImageNet. And then we use an infrastructure and architecture, it's called ResNet. Then we obtain a model. So the model, so any model has to be validated, okay? So if you are creating a predictive model, you need to validate it. So what we did is that we separated some of the images, we didn't put this into the analysis, and we check if our system is predicting well. So you can see these are correct. This line is, really correct predictions and some false positives and false negatives. So this is good, but it's not that good. So we wanted to increase the accuracy of the model. Since we cannot go to the field all the time, and field is also not safe, we come up with a new idea. What we did is that we went to the field, we modeled whole underground opening via virtual reality. So since virtual reality provides huge amount of realism, we use 3D models of the underground opening as a new feed to our model. So based on, so we use 360 synthetic hazardous roof images, because in our data set, hazardous images are low. Non-hazardous roof images are very easy to collect, and it was dominating our data set. And once we obtained this, we created different models. I'm not going to go into the details of it, but network D here reduced the false alarms and has some improvement. So this analysis showing us that there is a limit for prediction. Even you increase the number of data sets, we need more information to predict, but accuracies are not bad. Accuracies are, I don't have the accuracy values, but accuracies were around 95%. So 95% accuracy is actually very close to an autonomous operation. So this is actually the first model that we develop in this area to predict this. And if anyone is interested in developing these models, they are welcome to join the team. This work has completed. It was Ergin's PhD thesis. We collaborated with Makel. Makel is a professor in CU Boulder, who is a professor in cognitive sciences, because we need to understand some cognitive aspects of these detections. So he helped us. And if you are interested, this paper is published. So the next question is, can we predict methane in real time? Of course we can, if we have all the coal mine face is full of sensors. Unfortunately, it is not, because coal face is all the time moving, all the time dynamic, and we have a few sensors mounted on in the face. However, we have time-dependent behavior of the methane in a cold phase developed by numerical models. So how about using those numerical models for making a prediction? And we cannot do real-time prediction via numerical models because they are computationally really fast. So what we are doing in this project is that we are training our system with the numerical model results that are highly accurate, and then checking these are different models and their accuracies. I'm not going to go into the details of that. We are in the process of checking which model will work for real-time prediction. So this work is mainly done by Çağdaş, Dr. Brüm, Dr. Hogan, and Dr. Düzgün are helping us. So that's a collaborative work. That's another example of collaboration where we establish prediction models via collaboration of methane modeling and the data science. Okay, I have enough time. So SAFTI challenge started a few years ago. DARPA, Defense Advanced Research Agency, published a call. Call was asking to provide some systems to autonomously map the underground. And by that time, we team up with a really large number of students and faculty to address this challenge. So as you see, autonomy should be full. We should provide 3D mapping, and we should also provide networking so that the data will go to surface, and also the platform should be mobile. We were not selected to be funded for this challenge, but Minds were really generous, and they supported us to establish a course to develop algorithms and the platform to develop solution in parallel to the funded groups. So this was a really, really nice collaboration. I wish we could have these collaborations again. So we developed this system where we will have multimodal computing, multimodal energy, mobility, network, communication, and sensing. So I'm mainly involved in multimodal sensing part of it. And this is one example where we conducted in EDGAR, we collected lidar data from EDGAR by that time, and the system was automatically finding employers. So you'll see later on, the system is finding the bounding boxes of these employers in underground. So we did this research a few years ago. Now I have Jonas. Jonas is in the Zoom, probably he's listening. So he's updating the algorithm to improve its accuracy. And we recently conducted some tests in EDGAR with one of the platforms that we had. So that's another ongoing project. And these algorithms require some improvement all the time. And the lidar data that we had is not like the lidar data that you had from the autonomous cars. So how am I going to stop this? Okay, stopped. Let me stop this. Yeah, Audrey, I may need your help. Oh, okay. Cannot see it.
Can you just press the
Yeah, I did it. Yeah. So it's been such a long time that I'm not using Microsoft. Sorry for that. Okay, just a sec. No, it's yeah, why don't you go to the end? Yeah. Yeah, but I need to have an arrow here.
So now I think you need to press this.
No, this is not the arrow. Okay, just a second, let me solve this problem. Can you remove this? Okay, to stop share. Okay. Where's the screen? Okay, Google. Yeah. Yeah. Can you start screen sharing? Yeah. Okay, okay, can you go? Okay, so this project was done by Andrew Petruska from Mechanical Engineering, Chi Han, and Hao Zhang from Computer Science. Jim Moraga was helping us to develop these object detection models, and then Jonas handled the work. And I know Hakan and one of my postdocs, Hilal, involved in labeling the training images. And the last work that I'd like to share is that, can we help search and rescue people in underground via using the object detection plus augmented reality? When you have a disaster like fire, for example, in underground, it's really difficult to navigate. You need the boundaries of the underground opening. You need to know all these objects so that rescue people can navigate. So we developed an AR system, actually, to, can you see it? With a real-time mapping. So we have augmented reality goggles where this goggle is connected to a hard hat. That hard hat has certain sensors, for example, radar sensors, camera sensors, and all these sensors are processed, and the underground objects with the underground boundaries are sent to the augmented reality. We work with a really large number of students. Recently, this project is working on hardware integration. Chadash and other students work on developing the augmented reality. Maybe I can show. So yeah, this is interesting. Okay, so when you go to my website, you will see all these videos. These videos are there, and probably there is a latency issue, and those videos are not working here. But what you will see is that in the total darkness conditions, when you have the augmented reality goggles, you will see the underground mesh walls and with the detected objects so that you can navigate actually. So these are the work that I have been working since 2018. And I'd like to thank to all my team and all my colleagues for creating these exciting results and helping us to advance the research in helping the mining industry. So I'm happy to answer your questions.
There's 2 questions in the chat.
Okay. Okay, 2 questions. Yeah, you know, if you provide those images, we are happy to help you. The question is, could the lidar images provided by scanners on Sandvik autonomous LHDs and trucks be used instead of photos for roof fall detection parameters? Not every scan would need to be compared, but 2 per day. Yes, if you provide these data sets, we already have the algorithm, so we are happy to help. Yes, we can do that. And what's the other question?
If you go up.
Okay. Actually, yes, it calls. That's the reason why we establish, for example, shadows may create problems. That's the reason why we created a spatial light arrangement for underground, and we tested the performance of these light conditions in underground, how the shadows and different light conditions are changing the accuracy. That was part of the data augmentation. Yes, it calls, but there are ways to handle it, and that's what we handled. For example, we use really huge projectors that are used for providing light conditions in concerts or some underground, for some venues. And we use these kind of light conditions in underground. And I need to acknowledge help that we received from Robert Reeves. Robert Reeves is a great photographer. He do nighttime imaging, and he used these projectors, so we got great help from him by that time. Any other questions? Okay. So actually, there is no, in today's world, there is no single data source that you will get a good performance. The question is asking, instead of LiDAR, can we use sonar? Based on my 20 years experience in data analysis, it's always good to fuse the data, multimodal data, not either or, you use both. And actually in this Bat Vision project, we are using different sensors, for example, radar, LiDAR, camera. Of course, sonar could be used. That was one idea in the sub-T challenge, but sound data has, sound data requires huge amount of processing, and it may not help in real-time processing. Yeah, thank you for allowing me to advance the talk with your questions. This is excellent. So any questions from the audience here? Oh, great. So silence means, okay, we got it.
So I do, Shannon.
Yep.
And you're probably giving me too detailed an answer, but here's the deal. You have your data sets, and then you end up with your outputs. There has to be magic or computer programs or something else that goes on in between to make it all happen. Are those standardized programs, or are those ones that have to be developed for each application?
Oh, that's a great question, Steve. So the question is, when you have the inputs and when you have the outputs, in between you have the software and algorithms, are they standard or you do it on your own? Actually, that's the great question to answer the topic that I mentioned. People are coming to me and saying that, oh, we're going to use Python. Even though we use ResNet, for example, this is an established AI architecture, you need to tweak the model, and sometimes you need to change the whole algorithm. So all the models that we are developing are based on state of the art, but once we start doing that research, we realize that they don't fit our purposes. So we are changing the algorithm. So all these algorithms are not ready-made libraries that you can find in Google or Python. That's the reason why you need to understand the domain and also the algorithm so that you can make those tweaks. Thank you, Steve. Yeah, Jürgen?
Yeah, not so much a question, but maybe rather a comment. You talked about the project where we looked at explosive gas zones in longwall mine ventilation phases. And right now it takes 1 to 2 weeks to run a computational fluid dynamics model. and we are able to have the same prediction quality or similar prediction quality in 3 minutes with AI. So there's a huge difference, and this is something that we may be able at some point do in real time on the normal phase to build that into the share. So there's a huge difference. Even though AI takes a lot of processing, it's still not less than what the fluid dynamics model takes.
Oh, thank you. Was it clear by the Zoom audience? Do we need to repeat it? Could you just provide a feedback, thumbs up or down? What Dr. Brun said was clear.
I don't know if the remote audience could hear you.
Okay. Was it okay? It was good. Yeah. Thank you. Yeah. Thank you. Thanks for providing the link. I cannot keep track of the link, but can someone? Yeah. Thank you. Yeah. If not, then thank you for coming and providing interest to what we are doing. We are happy to collaborate with you in future. Thank you.
Thank you, Shabnam.
Yeah.
You brought the best turnout. About 70 people.
Yeah, I don't
Pretty
know.
good.
Thank you all, and we would like again to thank Professor Shabnam.
Yeah.
And see you next week.
Thank you. Oh, there's a raise hand.
This is like.
Oh.
Gotcha.
All right.
Yeah, thank you, I appreciate it.
Sure.